So what we've learned so far is that the change in energy, or more accurately put, the change in enthalpy for a chemical system can either be positive or negative. And we now know that the sign of that enthalpy change is just a function of the direction of the reaction. Are we releasing energy? In which case, if the system or the chemical system is releasing energy, then we're going to say that the delta H is negative, and heat flows from the system to the surroundings. That would be this negative direction here, so minus delta H. And we're also going to give that a new additional name. We're going to call that exothermic. So exothermic means heat flows from the system. We now know that we can also have this positive delta H, which means heat flows into the system from the surroundings, and that's used to drive the reaction uphill. So we'll drive it back up to a higher energy state, and we'll say that's the positive delta H, and we will say that's an endothermic system. And this is for chemical reactions specifically. So what we need to get into here, actually let's take a pause for a second. So let's think about this example that I have written up here. This is barium hydroxide with 8 waters attached to it in the solid structure. That's what this dot H2O, 8H2O means here. So that's a solid salt, barium hydroxide. If I mix that with this other solid, ammonium chloride, I yield these 3 products. And the overall standard enthalpy change, I should put a degree sign here, for the system is positive 83.3 kilojoules. Is this an exo or an endothermic reaction? Hopefully you look at this positive sign, you say that's endothermic. So what's happening to the system? Well, it means that if it's endothermic, heat is required for this reaction to run, right? It's going uphill, meaning this is plus heat on this reactant side. If heat is required to get this to go from here up to here, where does that heat have to come from? Well, it has to come from the surroundings. So if heat from the surroundings is taken to drive the reaction of this system, what happens to the temperature of the surroundings? Heat is being removed from the surroundings, right? It's being taken to drive this reaction. That should mean that the surroundings get colder, right? So the system itself is actually getting warmer because it's required for the reaction to go, but in doing so, the heat from the surroundings out here is being used to drive that reaction, which means the overall temp of the surroundings gets reduced. So this is a common cold pack. So if you've ever had an athletic injury and you need to ice things, this is the typical reaction. When you break that pack, you're releasing some of this barium hydroxide into a solution of ammonium chloride, and you're producing this reaction. That reaction requires heat to run. It requires exactly this amount of heat to run, which it steals from your body specifically. So if you have this laying on a knee, maybe your knee is sore, this reaction is going to run and it's going to steal the energy as heat from your knee, which is going to make the temperature of your knee decrease because of that heat transfer. Okay, looking at a second example here, I've got aluminum metal plus iron oxide or rust. Those two things can come together to create iron metal plus aluminum oxide. This reaction is, we talked about in a previous example way back, this reaction is a type of thermite reaction. What do we know about the sign of the standard enthalpy change here? Well, it's negative. So is heat being absorbed or released by the system? Hopefully you're getting fluent with this idea that negative means decrease in enthalpy. So heat is being released from the system. Where does that heat have to go? Well, it has to go to the surroundings out here, right? So does the surroundings get colder or warmer? Well, in this case, we would expect that the system is getting cooler, right? It's going from high to low, and in doing so, it releases this heat, which means the surrounding temperature gets warmer. Thermite, we will talk about this again later in this class, and maybe I'll show you a video. Thermite is a really common, highly exothermic reaction that people often use for the welding of railroad ties on site. So instead of having to bring out a huge torch to heat up something with, say, acetylene and oxygen into a remote place, what they can do is just carry a whole bucket full of aluminum powder and rust, and they can drive this thermite reaction, which gets so hot based on this enthalpy change. It's so hot that it produces liquid iron. And so you essentially have on-demand liquid iron, which is exactly what you need to weld railroad tracks together. So I'll show you a YouTube video of that, hopefully later in this chapter. So I think that's fairly intuitive for thinking about the enthalpy change and directionality and sign for chemical reactions. But what about physical changes in chemical species? Remember, physical properties are those that change without changing the molecular identity of the specific system. So an example would be the physical change or the phase change of water. So if you have water in this initial state here at minus 10 C, so you've got a cube of ice at minus 10 C, you could have that ice still in the same physical state but at a different temperature. And then you could convert that through a physical change from a solid state of ice to the liquid state of ice. So how should we think about each of those steps? Well, of course, to go from minus 10 C to 0 C, even though there's not a physical change, you're still changing the temperature of that object. And remember, the temperature is a proxy for heat. So heat is required to input into the system to affect that temperature change from minus 10 to 0. And then here in the second step, we'll say this is step 1 and step 2. In step 2, we're not changing the temperature of the system, but we are going from a block of ice where all the water molecules are arranged in a perfect crystal to water in a glass or in a beaker that can move around with lots of freedom. The temperature is the same, but we are breaking apart those bonds, not the physical bonds, not the covalent bonds, but how those molecules are arranged in space. There's still an interaction that's holding those molecules together. And so there's also going to be heat required for this phase change. We call this heat here, the second step, delta H. It is an enthalpy, but we specifically call it the enthalpy of fusion. Fusion referring to a phase change from solid to liquid. So solid to liquid means fusion, delta H of fusion, is the specific heat required to affect a phase change from solid to liquid. So we can look up the tabulated delta H standard of fusion of water specifically. We find out that has a value of 6.01 kilojoules per mole, and it's positive. So that means this is an endothermic process, the fusion process, which is also, we think about that as melting, which hopefully makes some sense, because if you've got, an ice cube and you want to turn that into a liquid, and this is water, you are going to have to put in heat into the system, right? Heat will have to go from the surroundings, and that means the overall energy change for the system is going to be positive, specifically positive 6.01 kilojoules for every 1 mole of the water that we started with. So it's an endothermic process to melt liquid ice from the perspective of the ice as the system. So to take that a step further, every phase change of any liquid or of any substance is going to have associated with it an enthalpy of that phase change. And so we started with this delta H of fusion, which the word fusion just refers to the solid to liquid phase change. And that's what we're seeing in this step one here. So we're taking ice and we're converting it to water. In that case, you're taking the crystal and you're breaking it into the liquid water. That requires a little bit of energy per mole, 6 kilojoules per mole. But if you wanted to go further in terms of the phase change, you could take that liquid and, think about a liquid. You've got molecules of water that are pretty close to each other, but they're not as close to each other as they were in the crystal. But in a gas form, you've essentially taken all of those molecules and completely separated them away. So you had liquid water where they were sort of associated with each other, but in gas water or gaseous water, the molecules are completely separate from each other. That's going to take quite a bit of energy, and that's what you see as a positive 40.7 kilojoules per mole, quite a bit more than it takes, quite a bit more energy than it takes just to melt water is boiling water, getting it to actually change phase. It's important to note here, though, that this boiling step, we call it delta H of vaporization or delta H of vapor. That has nothing to do with the temperature change of water. So the process of taking water, say from 0 degrees C to 100 degrees C, which is to the boiling point of water, that's not what this delta H of vaporization is referring to. This we could compute as a separate energy. We have to put heat to get the temperature to change from 0 to 100, but that's different than this step up here, right? That's to temperature change. What we're talking about here is the second step, which is just phase change, no temperature change. So it takes energy just to convert the physical state of that matter, not including the temperature change. So let's think about these 3 different examples, and I want you to pause the video and try to classify each of these scenarios as an endo or exothermic process. In each case, there's no chemical reaction that's occurring here, but there is a change in the physical state of a molecular or chemical species. So pause the video and see if you can rationalize exo or endothermic for each of the scenarios. All right, let's think about this first example, water freezing on lake in winter. So we can write out the physical change. So we're going from liquid water to solid water. So we want to think about the flow of energy, the direction of energy, and thinking about water here as the system. So let's draw a cross-section view of a pond or a lake. Right? This is the basin of the lake. Maybe this is you hanging out here. Great picture. And this is the lake itself, right? It's cold outside. This stuff is starting to freeze. The system here is the water itself. So the system is the water, so that's the perspective we're taking. The surroundings here is all of the other stuff, which would be the air, but also the ground around the water, you, and everything else. Okay, so if water is freezing on a lake in winter, we're going from liquid to solid, what's the direction of what's happening? Is this energy in or is this energy out? If we're going from liquid to solid, it means the system itself must be getting rid of some energy, right? We're going from water molecules like this in the lake that can all bounce around and move around as water to completely solid crystalline ice. So there must be a loss of heat from the original liquid water to get to here. We're decreasing in energy from the liquid to the solid form, right? So there must be some heat that's released from the liquid water from the system. So if the system itself, all of this water, is releasing heat to the surroundings, what do we call this type of reaction? It's an exothermic physical change. And that may feel non-intuitive, and that's why I want you to draw things out and really think about what is the system, what is the physical change, what's the direction, and is the system losing or gaining heat? Because in this case, the liquid water is losing heat, so it's an exothermic process. All right, so the second example is sweat evaporating from the skin on your surface of your body. So in that case, let's identify the physical change. I've written up here in green. So sweat is a liquid, water, and as it evaporates, the term evaporation implies vaporization, or the turning into of a gaseous state from the skin. So just like we did with the lake example, let's imagine this is the surface of your arm. So here's your hand, 1, 2, 3, 4, 5. So this is your arm. There's maybe your elbow. Got it? Okay, so you've got some big droplets of sweat right on the surface of your skin. And the system here, the perspective that we're taking, is going to be this water, this sweat on your body. And the surroundings are going to be your body and all the stuff around, right? All the stuff out here, wherever you're at. We know that from liquid to gas, do we have to put energy into the liquid to get it to a gas? Or do we need to remove energy from the liquid to get it to the gas? Hopefully you're saying, okay, I've got water molecules that are pretty closely spaced. In water, they're still free to move around, but in gas, you've got them completely separated from each other. That's the difference between a liquid and a gas. We've got to put energy in to the system to get it to look like this. So now this is plus heat to get this to work. So if heat has to flow into the system from the surroundings, now you're talking about your arm is supplying heat to each one of these droplets of sweat, right? So in this case, heat is coming into the system from your body and from the surroundings, but the really important part is the stuff coming from your body. So this becomes an endothermic process as we go uphill in energy. Heat is coming into the system. And this is why, so what happens to the temperature of your body, right? If your body is losing heat to drive this physical change on the surface of your skin, that means the overall temperature of your body starts to go down, right? And this is the whole mechanism of why and how we cool our bodies, is literally from the physical change and the net heat loss that our body affects by driving that liquid to vapor transition of water on our body. All right, last example, we've got magnesium sulfate, which is a solid salt, and we throw that into water. And this is one example of many different types of chemistries that hand warmers are made up of. And you'll see this in the Designing a Heat Pack lab that Dr. Harris will walk you through, or whoever you're taking this course from. So let's draw this out again, always. So you've got, let's just say, we'll just say you're building your heat pack in a beaker of water, just to keep it simple. But imagine this is just a bag. And you are going to toss in your solid magnesium sulfate here. And that magnesium sulfate is going to break apart into 2+ ions and sulfate ions. What do we think is going to happen here? Let's draw your hand. So this is your hand. Let's say your hand is just right on the edge of it. There's your hand. There's your arm. It's wrapping around this thing. That's your hand itself. So you're dissolving magnesium sulfate in the water as a hand warmer. If this is a hand warmer, then the system is again, it's going to be the chemical system. So it's the magnesium sulfate and water. The surroundings are going to be your hand and the universe, everything around it. If your hand is getting warmer, because this is a hand warmer, then heat is flowing from the system into your hand. So heat is being lost from the system, which means you're going from high to low. And if heat is being lost from the system, we're going to call this an exothermic type of reaction.